In this video, we'll take a look at section 9.3, significance tests with two means independent samples. So this is when you're comparing two different samples to see if the means are the same or to see if there is some sort of a difference. The first thing we're going to look at is what it means to be independent samples. First definition, two samples are independent if the sample values from one population are not related to or somehow naturally paired or matched with the sample values from the other population. Two samples are dependent or consist of matched pairs if the sample values are somehow matched. This is what we're going to do in the next section, 9.4, is looking at matched pairs. And the matching is based on some inherent relationship. That is, each pair of sample values consists of two measurements from the same subject, such as before, after, or pre-test, post-test, or each pair of sample values consists of matched pairs, such as husband-wife data, where the matching is based on some meaningful relationship. Some studies are done with twins, so that would be a matched pair as well. All right, let's look at our notation. We're going to have two populations. Mu1 is the population mean for the first population. Sigma subscript 1 is the population standard deviation. N1 is the size of the first sample. X bar 1 is the sample mean, and S1 is the sample standard deviation. And then the corresponding notations with the subscript of 2 apply to population 2. So let's look at an example. The question is, are we more creative with blue? In the chapter problem, we noted that researchers from the University of British Columbia conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the same task. Responses were scored by a panel of judges, and results from scores of creativity are given below. The researchers make the claim that blue enhances performance on a creative task. Test that claim using a 0.01 significance level. All right, we have our creativity scores for the red group. There were 35 people in that group. Their mean was 3.39 on their creativity score, with a standard deviation of 0.97. The blue background group had 36 people. Their mean creativity score was 3.97, and S is 0.63. So we can see that their scores are higher, but we want to see if they're statistically significantly higher. And what we're looking at, our level is 0.01. So that means if we look at the difference between the scores, are they far enough away from 0 to be considered unusual at the 0.01 level? All right, before we can run a hypothesis test, let's take a look and make sure that the requirements are met. The first requirement are the values of sigma 1 and sigma 1 and 2 are unknown, and we do not assume that they are equal. So we have two samples, and we do not know the population standard deviations of either. We just have S, which is the sample. The two samples are independent. I think it would be reasonable that the creativity scores for the red group don't affect the creativity scores from the blue group. They were two completely different sets of people. Both samples are simple random samples. We can go ahead and assume that they were. If the subjects with red and blue background might have been chosen, flip a coin. You take blue, you take red. All right, and then either or both of these conditions is satisfied. The two sample sizes are both large, N1 and N2 greater than 30, and they both are, or they come from populations having normal distributions. All right, so we have sample sizes large enough, so we're okay. All right, so now we can go ahead, since it satisfies the requirements of the test, then we can go ahead and run the test. So first thing we do is state the null and alternative hypothesis and make sure we identify what mean 1 and mean 2 is. These are the population means. So let's let mean 1 equal the mean creativity score with a red background, and then mean 2, the mean creativity score with the blue background, so that we don't get those confused. The null hypothesis, again, is just the statement of no difference. So the null hypothesis is that mean 1 is equal to mean 2, so that means that the creativity score with the red background and the mean creativity score with the blue background aren't different enough to be considered statistically significant. So no difference in creativity score based on color. Our alternative, we're trying to say up here, let's see, the claim was that blue enhances performance, and if we let mean 1 be red, that means that red would be less than blue. So the mean creativity score for red is less than mean creativity score for blue. All right, once we get all of the requirements out of the way, the null and alternative hypotheses set up, now we can go ahead and run our significance test. If you notice as we go, when we start getting a little bit further and have 2 sample means, the formulas get really complicated. So we're not using formulas at all. We're going to run these hypothesis tests using the TI calculator. We're going with technology and the p-value. So let's get our calculator. This hypothesis test is called a 2-sample t-test. So we hit our stat, go over to tests. 2-sample t-test on this calculator is option number 4. We don't have data, but if we did, we would put our actual data in list 1 and list 2, and then it would take care of the rest of the test here. We have statistics, so we're going to arrow over there, so that we are going to actually type in our mean and standard deviation and sample size from each population. So we decided that the red group was mean 1, so we're going to type in all the red group information. So we have a 3.39 for the mean, a standard deviation of 0.97 for the red group, and a sample size of 35. Then we move on to the blue group. They had a 3.97 mean score with a standard deviation of 0.63 and a sample size of 36. The next option is what is our alternative hypothesis? And ours is that mean 1 is less than mean 2. That's saying that the red group scored less than the blue group. Okay. Next, there's an option in here called pooled. We're not going to cover what pooled data, what we do when we pool our information. So our option is going to be no, and then click on calculate. Here are our results. The results are, let's see, the test is mean 1 less than mean 2. We get a test statistic t of a negative 2.9789, and that means that if we had a normal distribution with a mean of 0 in the middle, then the difference between these two is 2.9789 standard deviations below the mean. That means that basically the differences between the red they fall on the negative side. The p-value is a 0.002, and that represents the probability that happened by chance. Degrees of freedom are in here. Again, there's a formula for that. We don't need the formulas. And then all of the statistics are restated. So the 2 things that we really need, or the 1 thing that we need, is the p-value and the test statistic, because you'll be asked for that sometimes. All right, so our interpretation. The reasoning is the significance level of the test was set at 0.01, and our p-value was 0.002, which is less than the significance level. That means that there's a very small probability that we would get the results we did by chance alone. The difference between the red and the blue group was so far on the negative below, so much less that we were thinking that couldn't happen by chance. There's only a 0.002 chance that would happen, or a 0.2% chance. So we reject the null hypothesis and state our conclusion in favor of the alternative. So that's our reasoning. Our actual conclusion is there's sufficient evidence to support the claim that the red background group has a lower mean creativity score than the blue background group. And then I always include the p-value because we're using p-values for our conclusion. This supports the statement that blue enhances performance, but I just want to be careful here. The results don't mean that the blue background caused the higher score. It just means that people in the blue background room had a higher score. All right, that's our hypothesis test. The confidence interval with a 2-sample t. Again, we're going to run, let me get the calculator up here again. To get a confidence interval, what this does is it gives us, based on the difference between the means, it gives us an interval of what we think the true difference is between the means. So what we do is we choose a 2-sample t interval. Let me clear that out. So stat, over to tests, scroll down until you get 2-sample t interval. There it is. Statistics are what we're going to use. Notice it already has the sample statistics saved in there. And then as you get down here, the confidence level has to go with our significance level at the beginning. Okay, so our confidence level is going to be 98%. We're making a 98% confidence interval. The reason for this, it's a one-tailed test with a significance level of 0.01. The confidence interval needs the same area on both tails. So the other tail has a 0.01 area. So that means that in the middle, we would have 98%. So we have 1% on either side. And again, we're not going to talk about what pooled means. So that's a no. And then calculate. We get a confidence interval of negative 1.046, negative 0.1142. And what does that mean? Okay, keep in mind that's the based on our 2 samples when we take the difference between red and blue. This is we're 98% sure that this actually is the difference between red and blue. So if we take red minus blue, that means that red scored worse. Notice that 0 is not in that interval. So it predicts the true mean difference between the two as being negative. So our interpretation is we're 98% confident that the difference between the creativity scores of the red group and blue group is negative 1.06, and that should be 2 to 0.1142. These are both negative. Since the interval does not contain 0, the interval supports the claim that the mean creativity scores for the red group are less than the mean creativity scores for the blue group. All right, so just a note, again, we're going to omit the information from section 9.3, the alternative method used when population standard deviations are known, and pooling sample variances. And I did want to give you one note right here. If you do have a question that has actual data, what we would do is we would list these, determine which one we want to be mean 1, determine what we want to be mean 2, and then we would put sample 1 in list 1, sample 2 in list 2. Okay, let me go back. So that when you would go to stat, edit, and you would type the values into your lists. So if we have Pennsylvania as list 1 and New York as list 2, you would type the actual data in there. And then when you run your t-test, let's see our 2-sample t-test, when you choose data instead, then it will just identify where's your list 1, your list 2. List 1 goes with mean 1, list 2 goes with mean 2. Okay? All right, I hope that alleviates some stress of looking at the formulas in the textbook.